The sun is the most powerful and dynamic object in the solar system. Its energy sustains all life on Earth. Yet, its variability can also pose risks to the planet's technological and atmospheric systems. Modern science refers to these interactions as solar forcing, the influence of solar activity on Earth's environment. This relationship is complex. Changes in solar radiation, magnetic fields, and high-energy particles can alter atmospheric chemistry, disturb communications and satellites, and even play subtle roles in regional climate behavior. Understanding this variability has become an important scientific goal, especially as researchers observe signs that the sun may be entering a more active phase. Recent space weather reports and solar observations show that the sun's surface has entered a transitional period. Over the past several days, the frequency of solar flares has decreased and the rapid development of sunspots has slowed. The largest active regions are now mature or decaying. And by the start of next week, the most significant group will rotate to the far side of the sun. As that happens, the visible hemisphere will be left with only small, undeveloped spots. While this shift might appear to mark a calm phase, solar observers note that quieter surfaces often conceal deeper magnetic tension. The next stage of activity will likely involve plasma filaments and coronal holes, features that behave differently from typical sunspots, but are equally capable of influencing Earth's near-space environment. Filaments are elongated ribbons of dense plasma suspended above the sun's surface by magnetic fields. They appear stable, but under certain conditions, they can lose balance and erupt. These eruptions, known as coronal mass ejections or CMEs, expel billions of tons of charged particles into space. Unlike solar flares, which emit X-rays detectable by satellites in real time, filament eruptions often happen without warning. Their stealth makes them a continuing challenge for forecasters who monitor space weather and radiation hazards. At the same time, a medium-sized but perfectly equatorial coronal hole has opened on the sun's surface. Coronal holes are regions where magnetic field lines extend outward, allowing streams of high-speed solar winds to escape. As these streams travel toward Earth, they can compress the planet's magnetic field and produce geomagnetic storms. Such storms may trigger auroras at high latitudes, but can also disturb radio communication, satellite orbits, and electrical systems. For this reason, agencies such as NOAA and NASA's Space Weather Prediction Center will be closely watching this coronal hole and the movement of filaments over the next 7 to 10 days. The current pattern represents a typical stage in the solar cycle, a roughly 11-year oscillation between magnetic quiet and magnetic intensity. Yet, data collected over the past decade suggests that the sun's broader trend may be shifting towards stronger activity overall. According to a recent analysis from NASA's Jet Propulsion Laboratory, indicators such as sunspot number, flare frequency, and coronal emission intensity have all increased compared with earlier projections. The findings suggest that the current solar cycle may peak higher than expected, marking a rebound from the subdued cycles of the early 2000s. This conclusion supports warnings echoed by several scientific outlets. In a report from Live Science, NASA researchers described the sun as slowly waking up, emphasizing that increased activity could lead to more extreme space weather over the coming decades. Space weather refers to the conditions produced by solar eruptions, winds, and magnetic disturbances that propagate through the heliosphere, the vast magnetic bubble enclosing the solar system. When strong enough, these disturbances can affect human infrastructure. The article noted that modern society, with its reliance on satellites, navigation systems, and power grids, is more exposed to solar variability than at any time in history. Historical examples underscore this vulnerability. In 1989, a geomagnetic storm induced currents in the Hydro-Quebec power grid, causing a 9-hour blackout that left millions without electricity. The Halloween storms of 2003 disrupted airline navigation and forced satellites into safe mode. These events occurred during moderate phases of solar activity. A stronger storm under current technological conditions could have far-reaching consequences. Researchers therefore stress the importance of improving early warning systems and designing more resilient infrastructure as solar activity increases. Beyond its technological impact, The sun's changing behavior continues to draw attention for its possible influence on Earth's climate systems. Solar radiation and magnetic fields affect the upper atmosphere, altering temperature and circulation patterns that can cascade through lower layers. A study by Langmatz and colleagues presented at the American Geophysical Union examined how century-scale variations in solar forcing can affect tropical climate behavior. Using high-resolution climate models, the researchers found that even modest changes in solar irradiance can alter wind patterns, precipitation, and ocean-atmosphere interactions. These effects are nonlinear, operating through thresholds and feedbacks rather than direct proportional responses. This research helps explain why some regional climate records, such as those from the Tibetan Plateau, display abrupt transitions rather than gradual trends in response to solar variability. New analyses of paleoclimate data from Tibet show that temperature fluctuations align with solar cycles, but do not follow them smoothly. Instead, the climate appears to shift suddenly when certain thresholds in solar energy input or atmospheric dynamics are reached. These findings contribute to a growing recognition that solar influence acts as a modulator in the climate system, one that can amplify or suppress existing patterns depending on background conditions. The link between solar variability and Earth's magnetic field adds another dimension to this picture. A recently published study identified the first tropical evidence of the Greenland Sea and Vasto geomagnetic excursion, an event that occurred approximately 60,000 years ago. Previously, this temporary magnetic field collapse had only been documented at high latitudes. The new tropical record demonstrates that the field reduction was global, with intensity dropping to about 25% of its normal level. The event did not lead to a full polarity reversal, but it significantly weakened Earth's magnetic shield against solar and cosmic radiation. This discovery reinforces the idea that geomagnetic and solar processes can coincide to shape planetary conditions. In modern times, Earth's magnetic field is again weakening, albeit slowly. Measurements indicate a roughly 10% reduction in field strength over the past century. While not alarming in itself, this gradual decline decreases the planet's protection against solar particles. If a large coronal mass ejection were to strike during a period of reduced magnetic shielding, the effects could be amplified, producing stronger geomagnetic currents, more intense auroras, and greater radiation exposure for satellites and astronauts. Understanding these interactions requires direct observation of the sun's magnetic dynamics. NASA's Parker Solar Probe, launched in 2018, is providing unprecedented data by traveling closer to the sun than any previous spacecraft. Its instruments have revealed that magnetic recognition, the process by which magnetic field lines break and realign, occurs frequently and at smaller scales than previously observed. This process helps explain how the corona, the sun's outer atmosphere, maintains temperatures millions of degrees hotter than its surface. It also drives the acceleration of the solar wind, the continuous stream of charged particles flowing outward through the solar system. Complementary observations from the European Space ESA Solar Orbiter mission show that filaments can undergo repeated reconignation events before finally erupting. Each reconignation releases bursts of energy and reshapes local magnetic geometry, gradually destabilizing the structure. This behavior explains why some coronal mass ejections occur without accompanying flares. The energy buildup is distributed over multiple smaller events rather than a single explosive release. Such findings refine our understanding of the subtle mechanisms that govern solar eruptions and emphasize the need for improved forecasting methods. Predictive modeling has become a central focus of space weather research. Scientists at New York University Abu Dhabi recently developed an artificial intelligence system capable of forecasting solar wind speeds up to 4 days in advance. The model, trained on decades of observational data, has outperformed traditional physical models in initial testing. With further refinement, such predictive tools could give operators of satellites and power grids the lead time necessary to implement protective measures. The integration of machine learning into heliphysics marks a new phase of practical preparedness, translating complex solar dynamics into actionable information. NASA's long-term strategy also includes new missions to enhance continuous monitoring. The Interstellar Mapping and Acceleration Probe, IMAP, recently launched toward the first Lagrange point, will map charged particles from the Sun and interstellar space to better understand the boundary of the heliosphere. Together with the Deep Space Climate Observatory, DISCOVER, and the Solar and Heliospheric Observatory, SOHO, IMAP will form part of a multi-emission network designed to track solar eruptions from their origin to their arrival at Earth. The goal is to provide comprehensive real-time assessments of space weather conditions. As these efforts progress, a clearer picture of the Sun's behavior is emerging. The combination of fewer sunspots, increasing filament activity, and expanding coronal holes indicates that solar energy output is fluctuating in multiple ways. Although flare counts may be down, other indicators of magnetic reconfiguration are on the rise. This mixture of apparent calm and underlying dynamism is characteristic of transitional phases in solar cycles. Scientists expect that over the next several years, solar activity will intensify before gradually subsiding again as the cycle moves toward its next minimum. For Earth and its technological civilization, this means a heightened need for vigilance. The magnetosphere and atmosphere protect life from most solar radiation, but satellites, aircraft, and electrical networks remain exposed. Even moderate disturbances can cause operational disruptions or data errors. Space agencies, meteorological organizations, and research institutions are therefore expanding collaboration in heliphysics and space weather modeling. These cooperative networks aim to improve not only scientific understanding, but also practical resilience. Solar variability has always been a feature of Earth's environment. What distinguishes the present era is humanity's reliance on technologies sensitive to electromagnetic and radiation disturbances. The same processes that produce the aurora borealis also induce currents in power lines, interfere with radio communication, and degrade satellite electronics. By quantifying and anticipating these effects, scientists hope to turn what was once an unpredictable hazard into a manageable aspect of planetary weather. The relationship between solar activity, geomagnetic behavior, and climate underscores the interconnectedness of Earth's systems. Magnetic field fluctuations influence how solar energy enters the atmosphere, while atmospheric conditions in turn affect ionospheric currents and circulation. Each new observation contributes to a larger understanding of how the Sun's variability extends beyond astronomy into geophysics, meteorology, and technology. As of now, attention remains focused on the equatorial coronal hole and the series of plasma filaments crossing the solar disk. These features represent potential sources of moderate but sustained solar wind activity over the coming week. Monitoring them will help determine whether the current lull in flare activity persists or gives way to renewed eruptions. Every event contributes data that refine the models of solar dynamics and improve prediction accuracy for future cycles. In summary, the Sun is entering a more active stage characterized by subtle but significant magnetic restructuring. Observations of reduced flaring, increased filament formation, and emerging coronal holes correspond with the upward trend in overall solar activity reported by NASA and supported by independent analyses. Historical evidence, paleomagnetic records, and modern climate modeling all point to the same conclusion. Solar variability is a continuing driver of change across scales from the solar corona to Earth's atmosphere and technological systems. Understanding these processes is essential for anticipating both their risks and their broader scientific value. The Sun's fluctuations are not anomalies. They are expressions of a vast magnetic cycle that has shaped Earth's environment for billions of years. By studying these cycles with increasing precision, researchers gain not only tools for protecting infrastructure, but also deeper insight into the natural forces that sustain the planet.